Okay, class, good morning. This is Hydraulics 101. And we're going to have a look at some very simple concepts over here. And first of all, we'll have a look at right over here where we've got three submarines. Or if we like, we can call it one submarine and the submarine's moving around. All right. So first of all, the submarine is at the surface. If you notice at the surface there, it will be 101.3 kilopascals, so it's 1 atmosphere. The reason that the pressure is 1 atmosphere is because it's got 1 atmosphere of pressure at the surface. All right, this is because of the column of air that's above the submarine at the surface. The submarine dives down to 10 meters, which is about 33 feet, and down there measures the pressure, and the pressure turns out to be 2 atmospheres, which is 202.6 kilopascals. Dives down a bit further, dives down to 3 atmospheres, which is 20 meters down, and measures 303.9 kilopascals. Now, quite often we have mistakes when students are doing exams because they forget that there is actually an atmosphere already on the, that needs to be accounted for by the atmosphere. All right, so let's not forget that. So let's have a look now over here and see what's happening over here. So over here we've got a pipe and we've got 3 openings in it. And in the middle of it we have a valve. So we can open and shut this valve. Now we fill this is open to the air on both sides, and we fill this with water. Now, this little bit over here, this little elbow is very, very small. It's just enough so that we can actually physically put the, make this a reality in the experiment, okay? Because obviously that's not going to be easy to do. We've got to put an elbow there, and that elbow will come up a little distance, but it is so negligible that it makes no difference, okay? So, that's open to the air on that side, it's open to the air on this side. We fill it with water, and lo and behold, the water will not flow from either end. Okay, the pressure at each end is equal. This is the very point of why it's good to use water as a leveling tool over a short distance. Okay, over a very, very long distance, obviously that won't be the case because water is not going to be level over a very, very long distance. But in a short distance, like in a building project, for instance, the water will be level at both sides, so you can count on it, you can use it to level your building with. Okay, it provides a short distance. Okay, so that's number one. The point here is the water will not flow out of either end, and the pressure at either end is equal. The pressure at either end will be 101.3 kilopascals. Okay, so 1 atmosphere. Now we have a look at scenario number 2. So scenario number 2 is the same deal as up here, except we've opened the middle valve. And the purpose for opening the middle valve is to see, does it make any difference? Is this water that's in here halfway, is that halfway making any difference? Will it shoot out of the middle? Okay, will the mass of the water or any other thing force water to be shot out the middle? Well, same deal, open up the middle valve and still the water will not flow. So the pressure at each opening will be equal. So there'll be 1 atmosphere here, 1 atmosphere here, 1 atmosphere here. Okay, now let's have a look at scenario number 3. So number 3 is exactly the same deal, except this time we've put a 10-meter standpipe. We've attached it to this one end. Again, it's still open to the atmosphere. And on the other end, we've put a gauge. The gauge measures how many meters of head. Okay, so that can also be converted to kilopascals, all right, which is so for every 10 meters, that's videos on. So for every 10 meters, that's 1 atmosphere. Okay, so the gauge is designed to measure the amount of meters of head, and it's actually measuring pressure.
What is head?
Okay, head is if you like the amount of water above the atmospheric pressure. In other words, how much water is sitting above the surface. For instance, the reason that they make a water tower so high, in fact, they don't make it too high. Okay, they make the water tower so high is because they want to be able to have that pressure distribute the water through the town. Okay, so you need to make a very high water tower. In fact, the higher you make the water tower, the more pressure everybody gets in the town. So obviously there's a limit to what height you want, because you don't want to damage everybody's equipment, and you certainly don't want to spend lots of money. Everybody spend lots of money having pressure reducing valves so that their equipment doesn't get damaged.
But Phil, how do you get the water up there in the first place?
Okay, well, that's another issue, because that now takes energy to work against gravity. So gravity is what's causing the water to go up. You need energy to lift the water up. So the pump needs to be able to lift the water up that 10 meters, so that we've got 10 meters of head above the ground. Yeah. So that's the potential energy then, is 10 meters of head above the ground. And then as you open up the faucet, then out pops the water, and that water will flow at the pressure that is at the top of that tower. Okay, that's how it works. That's why we have water towers. If the only thing that could cause the pressure was the length of the pipe, we wouldn't need a water tower, would we? Just make more length, more pressure. Well, that's ridiculous. You need the water tower in order to be able to have the pressure. And the only pressure that's available to each person has got to do with how high that water tower is. Okay, so now there are some little bit of provisos in here, and that is, for instance, in a town we have head loss because of bends. So quite often, so you might, for instance, sometimes you turn on a water, you can hear a knocking sound. That knocking sound is called water hammer. And water hammer has got to do with the bends, that the water's got to knock against that bend, and it causes...
I do the exact same thing at home when I turn the shower on.
When you turn the shower on, yes, exactly. So you get...
It evens out after a while, but
yeah,
how do I stop that?
You do. So if you open the faucet quickly, then you're likely to get the water hammer. Just do it very, very slowly, and you won't get the water hammer. Okay? So that's one. Now be careful, don't open it quickly, because that water hammer is actually a force. All right? That force can actually blow apart the bend. Okay? It's sufficient to blow that apart. So you'd be very, very careful, otherwise you can cause some very expensive damage in your house. So be careful. And again, it's got to do with the design. So plumbers who design the layout in the reticulation layout in your house ought to be thinking about water hammer. Okay. And now the other thing that you can do is you can get yourself a valve for the faucet that actually that can actually reduce water hammer, or you can actually buy an inline valve that's designed to reduce water hammer, so it'll take the brunt of that force. Okay, now, so let's have a look. So I've said here, introduce a vertical standpipe 10 meters long, close the middle valve, and put a pressure gauge over the other end. So there's the pressure gauge. The pressure will read 10 meters of head. Okay, it will not read 20 meters because of this extra 10 meters that's here in the pipe. That will be irrelevant. It's only got to do with how much head there is. Okay, now, so the gauge has already been tagged and zeroed, in other words. so that will ignore the pressure. That's why it's going to read 10. If the gauge was not zeroed and for some reason or other it needed to read the atmospheric pressure, well, it would therefore read 20 because of the atmospheric pressure at this point. However, it's zeroed, it's only going to read this 10 meters ahead over here, regardless of how long this other pipe is. This pipe here can go to Kingdom Come. That pressure over there will still read 10 meters. That's how reticulation of water supply works. Okay, now, so my question is, this is the question I want you to answer. Why do we only get 10 meters of atmospheric 10 meters of pressure at this end over here? Why do we only get 10 meters? Why don't we get the other 10 meters? Why don't we get the whole length of the pipe? Why is it? Okay? All right, so in other words, what are we actually looking at? All right, so now remember about gravity, mass. In order to get force, F equals mg, and this component, thank you, this component of force only happens when there is mass associated with it. Okay, so I've heard situations where people say, well, gravity is not a force, therefore throw it out. Yes, I would laugh too, because I mean, we use it for all sorts of things in everyday life. We use it with remarkable precision. So obviously it is a useful tool for us. So, however, when we describe the force of gravity, what we actually mean is the force in combination with the mass. Okay, in Einstein's general relativity, mass is intrinsic to the bending of space-time. Okay, so from Einstein's point of view, mass bends the space-time. That bending of the space-time and the objects falling into, if you like, into the well of space-time, that is now those two together, which becomes apparent as a force. And to all the world looks to us, when we look at it, as a force. We use Newton's equations, because Newton very carefully worked out how this worked. Well, he didn't work out how gravity works, but Newton told us in what way gravity would work. For instance, in projectile motion, Newton was able to tell us, well, we can predict not only how high an object will go if we throw it, but it will also predict how far it will go and where it will land, and how long it will take to get there. All of these things are as a result of Newton's equations, and they involve gravity. So the fact that Newton himself didn't understand what causes the thing to fall, he didn't understand that bit. He most certainly did understand what would happen if you dropped it. And he could use those equations with remarkable precision for all sorts of things. Right up till today, we still use them. Satellites are where they are because of Newton and Kepler and the like, okay? The fact that these people didn't understand what exactly causes gravity to things to fall is irrelevant. The fact is, they knew what would happen under certain conditions and what it would do under certain conditions, okay? All right, so have a look at this. I want you to make sure that you understand this principle, okay? And then we can, this is certainly part of, I think there's probably about 2 questions in the test with respect to this. It's pretty simple. I don't think there's much they can ask you that you wouldn't understand, okay? All right, no problems.